Hello, my name's Roger Watson and welcome to this session on theories and methods in quantitative research. Quantitative research is concerned with measurement, and measurement is something that we're all concerned with in our everyday life. We measure weights and volumes and heights regularly, almost without thinking about it. In relation to measurement, Lord Kelvin said, "To measure is to know. If you cannot measure it, you cannot improve it." The first thing I want to do is introduce you to levels of measurement based on Stephen's theory of scale types. And Stephen's proposed 4 scale types: nominal, ordinal, interval and ratio. These are now commonly used, but it is just a theory. And there's an excellent paper in Science on the theory of scale types, which is well worth finding and reading. First of all, nominal levels of measurement. These are purely descriptive, or the categorical use of numbers. For example, diagnosis could be 1 for coronary heart disease or 2 for chronic obstructive airways disease. Sex could be 1 for male, 2 for female. Nationality could be 1 for Spanish, 2 for British, 3 for Italian. Note that in nominal levels of measurement, the numbers have no relative value. To be female means that you're not twice as good or half as good as a man. It's simply a number being used to assign you to a category. Next, ordinal levels of measurement. These are data which can be categorized and ordered. For example, feeling better, feeling the same, feeling worse. These could be given the numbers 3, 2 and 1, and the numbers have an obvious meaning. But note that the interval between the numbers is not the same. Moving from feeling better to feeling the same is not half as good or half as bad. However, the numbers do mean something relative to one another, but note that the numbers could run in any direction. You could number feeling better 1, feeling the same 2, and feeling worse 3. Next, the interval level of measurement. These are data which can be categorized, ordered, and where the intervals between the data mean the same. The classic example here is the centigrade temperature scale. But interval scales do not have a true 0 point, so 0 on a centigrade measurement scale is an arbitrary 0. It just happens to be the temperature at which water freezes. According to this theory of measurement, ratio level measurement is the highest level of measurement. These are data which can be categorized, ordered, and where the intervals between the data mean the same, and which have a true 0 point. And these are the sort of everyday measures we use, for example, height, weight and time. So we can order all these in a chart. Here are the characteristics of levels of measurement. We can classify them in terms of whether they classify, order, have equal units or absolute 0. Nominal only classifies, ordinal classifies and orders, interval classifies, orders and has equal units, and ratio classifies, orders, has equal units and has an absolute 0. The point behind this, which is something that you'll come to later as you do more quantitative research and begin to use statistical methods, is that the type of data dictates what type of statistical test you use. Next, I want to look at something that's very important in measurement, which is error, and then estimation and chance. Measurement is concerned with precision, but it's against a background of error, estimation, in other words, the confidence we can have in our measurements, and also largely an element of chance is involved, or probability. So I'm going to look at all of these in turn. Next, let's look at error in measurement and the sources of error. These can be either systematic or random. Systematic errors are errors that occur every time you make that measurement, and they're the same every time. Systematic errors can be eliminated to some extent by making the instruments you're using as accurate as possible, because systematic error is concerned with instrument error. Random error, on the other hand, is to do with humans who either make estimations or respond to questionnaires, and you can overcome human error to some extent by training people to make better measurements or informing them how best to respond to a questionnaire. But please note that you can never eliminate either systematic or random error. And instrument error can be between instruments or within instruments. Between instruments means that if you use two different instruments to make a measurement, it won't give you exactly the same measurement. Within instrument means that every time you use the same instrument, it doesn't give you quite the same measurement. And exactly the same applies to human error, between people and within people. Next, estimation. Now this is something we do all the time, almost without thinking. We're always estimating how far away something is, or how much something will cost, or how much something weighs. Something we don't often realise is that the greater the precision with which we try to estimate something, the lower the confidence in that measure. For example, if I try to estimate how far away the house across the road is, I guess it's 10 to 15 metres away. And if I say it's 10 to 15 metres away, I'm 100% accurate in that estimation, because it is 10 to 15 metres away, but I don't know exactly how much. If I try to become more precise by saying it's exactly 11 metres or 11.5, or get it down to the nearest centimetre, I can be far less confident. Now this concept of confidence is something that you will encounter later when you come to doing statistical analysis, and it is specifically expressed in something called confidence intervals. Next, the concept of chance, or probability as it's more accurately referred to. This has to be taken into account in all measurement, especially related to research. We need to know if our results have occurred by chance or not, and that is what statistics is concerned with. We're not going to look at any statistics here in any detail, but I do want to explain as best I can what probability means and why we take it into account. Probability is expressed as p, usually large P, and it always lies between 0 and 1. In fact, it's always greater than 0 and less than 1. In theory, it's not possible to have a probability of 0 or a probability of 1. There's always some chance of something happening, and it never happens all the time. So to demonstrate this, what do you think your chances are of getting across Alligator Creek? Okay, there's the alligator. What I'm saying is you've got some imperative to get to the other side. You have to get there. There's either a reward when you get there, or there's danger of a greater kind if you don't go across. So, let's say, would you cross Alligator Creek for £1 million? Would you swim over if your chances of being eaten were 99%? I'm sure you wouldn't. Would you swim over if they were 95%? I don't think you would. Or 90%? What about 50%? You might begin to think about it. What about 40%? What about 30%? What if it were only 10% or 5%? Okay, so the lower the probability of you being eaten, 5% is expressed as p equals 0.05, then I think the greater the likelihood that you would try to swim across and get that money. So let's apply that to a randomized controlled trial of treatment A against usual treatment. If treatment A proved to be better than treatment B, would you accept that if the probability of the outcome was 99%, 50%, or whatever, all the way down to 1%? Well, if you understand probability, you should be looking for a low probability, because a high probability tells you that that result was likely to take place anyway, in other words, by chance. If I tell you that p is something like 0.05 or 0.01, I'm indicating a very low probability that the outcome occurred by chance. In other words, what I'm telling you is that the outcome occurred as a result of what I did, the intervention. So let's take a look at measurement in social sciences. Again, this is concerned with precision, but against a background of error, estimation and chance, just like any other kind of measurement. Measurement in social science is not concerned with measuring physical properties, but with measuring latent variables, either people's states at the time or their traits, which are more long-term. Things like attitudes, symptoms, psychological morbidity such as stress or burnout, personality, satisfaction and so forth. There's almost no end to what people try to measure in social sciences. Now, reliability and validity are not unique to social science measurements, but they're much more acute here because of the difficulties in making the measurement. These can be easily checked with physical measurements, but they need to be established for measures in social science, and this is called psychometrics. Reliability, first of all. If an instrument is reliable, it gives the same measurement every time it's used. Okay, there's a ruler which looks like it's 12 inches. There's one which also looks like it's 12 inches. They both give a reliable measure. They give the same measure each time they are used. However, as you can well tell, one of those, or possibly both of them, is wrong. So reliability is only part of the story. Validity. An instrument's valid if it measures what it purports to measure. So in other words, only one of these can actually be valid or correct, and we need to have some other way of estimating that. Now, these targets, which have been used for target practice, can be used to demonstrate reliability and validity. On the top left, if the bullets had hit the centre of the target, that would be considered valid, but of course they haven't, so it's not valid, and their shots are all over the place, so they're unreliable. Top right, these are unreliable because they're all over the place, but they've covered the target widely and including the centre of the target, so that measurement is considered to be valid. Bottom left, the dots are very close together, the shots are very close together, so that is a very reliable shot. However, it's not valid because it's nowhere near the centre of the target. And bottom right, that measurement is both reliable and valid because it hits the centre of the target and the shots are clustered in one place. Now, questionnaires, which are used to measure latent traits, are the backbone of the social sciences, really, and they're composed of a series of questions or items, and these are commonly answered using Likert type scales. For example, strongly agree, agree, don't know, disagree, or strongly agree, numbered 1 to 5 respectively. They could also be numbered the other way around. You'll recognise that as an ordinal scale. The assumptions of measurement in social research are that measurements are unidimensional. That means that measures measure the same thing, that a set of items in a questionnaire measures the same thing, or not, as the case may be, but there are techniques, statistical techniques we can use to investigate that. Also, this rather clumsy phrase that they're locally stochastically independent. This applies to all measurement. It means that the items are being responded to because of the underlying latent trait, that they're not being responded to because of the response to a previous item. So, for example, if I ask if someone in a scale for depression is either feeling suicidal or doesn't feel like getting out of bed, they answer the either question based on how they feel. However, if I ask somebody if they can walk 5 yards or 10 yards or 20 yards, sorry, I should be saying meters, 5, 10 or 20 meters, clearly somebody who walks 20 meters can walk 5 and 10. They're not independent. That's a very rapid explanation of that. So there are essentially two approaches to reliability and validity. Classical test theory and item response theory, and we're not going to go into either of these in great detail here, and we're not going to look at item response theory examples here at all. But, just to differentiate them, classical test theory treats items on a Likert scale as if they were all equally difficult, whereas item response theory does not assume that items have the same level of difficulty. This means, for example, that in a range of items on a questionnaire in classical test theory, it assumes that the answers to the questions are more or less random, although if you sum up the scores to the answers, it gives a measure of the latent trait. Item response theory doesn't assume that. It assumes that there's some relationship between the response to an item and the level of the latent trait, and that's the difference. We'll leave that there at the moment. There are other sessions available on factor analysis, which is one of the classical test theory methods, and there are sessions available on item response theory. Classical test theory methods are based on correlation. Methods such as Cronbach's alpha and factor analysis, and item response theory methods are based on methods like rash analysis and Mochen scaling. So, turning to the classical test theory methods, Cronbach's alpha and factor analysis. What is a correlation? A correlation is a statistical measurement of the relationship, either positive or negative, between two variables. So, for example, these are correlations. Number of hours revising should be positively related to exam results. Flu jabs given should be negatively related to people with flu. The line, which is the line of best fit for those particular points in those graphs, is described as the line of correlation. So, establishing reliability. There are various methods here: internal consistency, test-retest, intra-rater and inter-rater reliability. Internal consistency is a measure of whether all the items in a questionnaire or in a group of items, a subdivision of a questionnaire, are measuring the same thing. In other words, are they unidimensional? The classic method here is Cronbach's alpha, although it does have its limitations. Test-retest is, for example, testing an exam. For example, you could give it to a group one day and give it to them a day later or a week later, and then you look at the correlation between the two sets of results. We use intra-class correlations to measure this. Intra-rater reliability is a measurement when you use a rating scale, and when you ask somebody to rate something on one occasion and then to rate it again later. Again, we use intra-class correlations. And for inter-rater reliability, we ask two people to rate something and we correlate their measures, and that again is measured using intra-class correlation. 2 1s and 1 1 in the brackets indicates the kind of model that you need to use for intra-class correlation. We can't go into that in detail here, but you can choose these in most statistical packages. Validity is composed of construct validity, which is the highest form of validity, but essentially it's unobtainable because we can never know everything there is to know about a construct, but it's broken down into face validity, content validity, factorial validity and criterion validity, which is subdivided into concurrent and predictive validity, and finally convergent validity or discriminant validity. We'll go through these slowly. Face validity, there are no formal criteria for this. This is really a sense of giving a questionnaire to people to read to make sure that they can read it and understand it and that it makes sense. On the other hand, for content validity, there are specific criteria. There's a paper by Lin, a classic paper in nursing research, on the determination and quantification of content validity, and it describes the use of a content validity index. So you can actually get people to rate the content of a questionnaire, and you can actually measure that rating and decide at which point agreement is sufficient to merit use of either individual items or the whole questionnaire. Factorial validity is investigated using factor analysis, and you may want to read this paper in the Journal of Advanced Nursing, which outlines some of the best practices in factor analysis. Just to explain what factor analysis does, I'll exemplify this with my own research. And using an example from my own research, the Edinburgh Feeding Evaluation and Dementia Scale, I'll very quickly show you what factor analysis does. This is a scale which is responded to on a 3-point scale, and if you factor analyse it, you find that there are 3 underlying dimensions: one of supervision and physical help, which is nursing intervention; one of leaving food on the plate and spillage, which is the observational dimension of feeding difficulty; and then 6 behavioural items. So that, very simply put, is what factor analysis does. There are other sessions available on factor analysis, and I won't go into item response theory here in any detail because there are other sessions on item response theory that you can look at. Criterion validity and convergent and divergent validity. Our approach through concurrent validity. This is correlation with a measure of the same phenomenon, something contemporaneous, done at the same time. So, for example, one depression scale could be correlated with another. Predictive validity is correlation with another measure at a later time. In other words, does the level of depression or does the level of quality of life, for example, predict depression at some later point? Convergent and divergent are similarly correlation or lack of correlation with measures of other phenomena predicted to correlate or not correlate with some new scale that you're developing. These are quite complicated, and I have to emphasize that they are rarely all done for any particular scale. And finally, discriminant validity is the ability to discriminate between cases, for example, severe and mild or no case, and we can use correlation or t-tests here, which are fairly simple statistical tests. Please note that the construct validity of no scale has ever been fully established. All the tests described here have rarely been done for one scale, and that psychometric work often takes many years, and I'm talking about 10, 15 or 20 years. Next, let's move on to sensitivity and specificity. These are often not associated with the psychometrics of questionnaires, but they're very important for diagnostic questionnaires, and it's very important that you have some understanding. Basically, where you can relate the score on a diagnostic questionnaire to a specific diagnosis or test, then you can measure the sensitivity or specificity. It has to be yes or no. Has the person got the disease or not? And it has to be a definitive diagnosis. So, for example, imagine a study evaluating a new test that screens people for a disease. Each person taking the test either has or does not have the disease. The test outcome can be positive, predicting the person has the disease, or negative, predicting that the person does not have the disease. The test results for each subject may or may not match the subject's actual status, in other words, when they're actually diagnosed. So we want to know how well that questionnaire predicts that people have the disease, or doesn't predict it, or predicts wrongly that they have the disease in fact. And this is measured using sensitivity and specificity. So we can have true positives, sick people correctly diagnosed as sick, or false positives, healthy people incorrectly identified as sick. True negatives, healthy people correctly identified as healthy, or false negatives, sick people incorrectly identified as healthy. So to summarise, true positives are correctly identified, false positives are incorrectly identified, true negatives are correctly rejected, and false negatives are incorrectly rejected. And sensitivity is expressed in this mathematical equation. It's the number of true positives over the number of true positives plus the number of false negatives. And this gives the probability of a positive test if the patient really is ill. Specificity is the number of true negatives over the number of true negatives plus the number of false positives, and this gives the probability of a test given that the patient is actually well. What I'm going to get to here is a demonstration of how sensitivity and specificity are traded off against one another. In other words, the higher the sensitivity, usually the lower the specificity, and vice versa. So here, for example, we've got high sensitivity on the left and low specificity on the right, The test on the left is highly sensitive because there are few false negatives in blue. Those are the people who failed the test. In other words, those are the people who've got the diagnosis. On the right, there are many false positives. It has low specificity. Those are the people who haven't got the diagnosis. So on the right, those people in red are people who've been wrongly diagnosed as having the disease. Alternatively, on the left, we've got low sensitivity traded off against high specificity, and it's the opposite way around. On the left, there are many false negatives. In other words, we've missed many people who do have the disease, and on the right, we've got few false positives. We haven't wrongly identified people. So they are a trade-off against each other. And that's rather nicely demonstrated in this graph and in the next one. Here you can see that on the left you've got the people without the disease, and on the right the people with the disease. There are two different distributions, and you can see what proportion is described as the true negatives and the ones that are described as the true positives, and also the false negatives and the false positives. Clearly, the further apart these two graphs are, or the further the true negatives are to the left and the true positives with the disease are to the right, then the lower that region in the middle of false negatives and false positives. But notice that in theory they always overlap. So here you can see the trade-off between sensitivity and specificity. The higher the specificity on the right, the lower the sensitivity, and vice versa on the left. Sensitivity and specificity can be plotted together to provide a receiver operating characteristic curve, and we do it as follows. On the y-axis we plot the sensitivity, which is the true positive rate, and on the x-axis we plot the false positive rate, or 100 minus the specificity. If the line falls where the dotted line is, it tells you that using your questionnaire is no better than guessing the outcome in terms of the diagnosis. If the curve falls below that, it's worse than guessing. However, any curve falling above that line is indicating that the questionnaire may be useful in terms of the combined sensitivity and specificity, and it's the area under the curve that we use, and that should be a minimum of 70% to indicate that the combined sensitivity and specificity of the questionnaire is any good. So thank you very much for listening. That's my email for any questions or comments, and you can follow me on Twitter. Once again, thank you very much for listening.